Hello and welcome to a differential equation experiment. So what we're going to be doing today is we're going to be measuring the temperature of some water. The kettle is just on its way to boiling at the moment. Currently room temperature is very cold, it's 15.7 degrees. We're just waiting for the kettle to boil and then we can start our experiment. What we're going to be doing is tracing the temperature of the water as it cools and finding out if it does indeed obey an exponential law. As soon as the water boils, I'll pour it into the cup, we'll find out the initial temperature and I'll set the probe to collect data. After 5 minutes we'll record the temperature and then from there we should be able to work out or predict what the temperature should be after 20 minutes. The water's just coming to the boil now. In goes the probe and we start collecting data. The probe looks like it was a bit confused at the beginning, so we'll start from 1 minute at 89.7 degrees and we'll run the experiment for 21 minutes. Okay, here's the maths bit. A liquid cools at a rate proportional to its temperature above room temperature, which I'm calling theta. So our differential equation is d theta by dt, that's the rate of change of temperature, equals minus k theta. K is the constant of proportionality, theta is the temperature above room temperature, and I put a minus sign because the gradient is negative, because it's cooling. So our differential equation, the integral of 1 over theta d theta equals minus the integral of k dt, getting all the thetas on the left and all the t's on the right. When we integrate we get ln theta on the left equals minus kt plus c, where c is our constant of integration. The original conditions, when t is 0, theta is theta 0, which is the notation I'm using for the initial temperature above room temperature. So we stick in theta 0 for theta, we stick in 0 for t, and we find out that c, the constant of integration, is ln theta 0. Substituting that back in, we have ln theta is minus kt plus ln theta. If we get all our logarithms on the left, we can get a minus sign, and then we can write ln theta over theta 0 equals minus kt. Then we exponentiate both sides, so theta over theta 0 is e to the minus kt, and then we finish off by timesing by theta 0, so we have theta equals theta 0 e to the minus kt. And that's the rule we're going to be using to test our experiment. So our initial temperature, 89.7, room temperature was 15.6, giving us a difference of 74.1. So the temperature is 74.1 degrees above room temperature. So we're going to be using the formula theta for the temperature is 74.1 e to the minus kt, and we're just waiting until the time gets to 6 to record a new temperature, and then we can work out what k is. The mug you might notice is a Fozzie Bear mug, the Muppet movie coming out this week. And there we go, there's our time, 6 minutes and a temperature of 79.7 degrees. So after 5 minutes, the temperature above room temperature was 64.1 degrees, so it's gone down exactly 10 degrees in those 5 minutes. So using the formula we have 64.1 equals 74.1 e to the minus k times 5. Dividing by 74.1 we have e to the minus 5k is 64.1 over 74.1. We take logs of both sides and divide by minus 5, and that gives us a k value of 0.02899. So using our value of t for 20 minutes, we should expect the temperature above room temperature to be 41.5 degrees. Adding on our 15.6, we expect the water to be at 57.1 degrees centigrade. So 1 minute left, we're trying to get 57.1, we've got about 5.5 degrees left to go. And there we go. 21 minutes on the clock. That's 20 minutes since we started. 61.7 degrees. That's about 4 degrees hotter than integration would suggest. Whoops.